So, welcome students for the chemistry lecture. And yesterday you learned the factors affecting quantum yield. There are four factors. First, it is the temperature. Second, it is the intensity of light absorbed. Third factor, it is the wavelength. And fourth factor, it is the addition of inert gases. And due to addition of inert gases to the reactants, the quantum efficiency increases, and the intensity also plays important role because the quantum yield, it depends on the intensity of the light absorbed. Again, the wavelength, shorter the wavelength, greater is the energy, and the absorbed light, it matters a lot for the chemical change. So wavelength, it is another factor which affects the quantum yield, and temperature, it plays important role in the reactions, and here quantum yield increases with temperature. Then you have seen the photosensitized reactions, and photosensitized reactions are the reactions which occurs due to the addition of sensitizer, any sensitizer, because the reacting molecule is photochemically inactive and it is not able to absorb the light radiation, and for that purpose, if we add any external sensitizer which is able to absorb the light radiation, then and then a photochemical reaction takes place. For example, the dissociation of hydrogen. Here, the UV light of wavelength 2537 angstrom does not dissociate hydrogen because it has more energy than the dissociation energy required for the hydrogen molecule, because here the hydrogen molecule is photochemically inactive. It is not able to absorb the light radiation of wavelength 2537, though this wavelength has a greater energy which is needed for the dissociation of hydrogen molecule. But if we add a small amount of mercury vapor, then that mercury vapor, it absorbs the light radiation and it becomes a excited one. This is the primary process. Excitation of mercury, it is the primary process, and in the secondary process, the excited mercury, it transfers its excess energy to the dissociation of hydrogen molecule. Here the mercury, it acts as a sensitizer, and the dissociation of hydrogen molecule takes place and it forms two hydrogen atoms. Then the second example, it is the photosynthesis, and all of you know, in the photosynthesis reaction, chlorophyll, it acts as a sensitizer, and in presence of CO2 and sunlight, here plants, they produces the carbohydrates and oxygen. This is the two examples of photosensitized reactions. A simple meaning of here photosensitization, it is due to addition of external photochemically active substance the chemical reaction or photochemical reaction takes place here. Then the here another example of photochemical reaction, it is the photochemical equilibrium or the photodimerization of anthracene or polymerization of anthracene. And this polymerization of anthracene or dimerization of anthracene, it is the example of photochemical equilibrium reaction. And here in this, the photochemical equilibrium means it is the state in which system has higher concentration that of product earlier than it had in the equilibrium state. When a solution of anthracene in benzene or toluene is exposed to UV light, it polymerizes to dianthracene, and in the dark the reverse reaction takes place. That means when we take the solution of anthracene in either benzene or toluene, in the forward reaction the formation of dianthracene takes place and the equilibrium between the reactant and product, it disturbs, and as the concentration of product increases, the rate of reverse reaction it also increases, and then the equilibrium will be established. So the photochemical equilibrium state is the state in which system has higher concentration of product earlier than it had in the equilibrium state. After some time, a stationary state will be reached. In a primary process, the excitation of anthracene occurs. That means C14H10, that is the anthracene, by absorption of one photon, it becomes excited one. And this excited molecule, it collides with another ordinary molecule of anthracene to form a dianthracene, and the quantum yield of this reaction it must be 2 because due to the absorption of one photon, two molecules of anthracene they are reacted, but in actual practice the quantum yield it is low and it is about 0.5, and the reason for this is the fluorescence occurs at the low concentration here, and due to the fluorescence the quantum yield decreases. A concentration of anthracene increases and fluorescence decreases and quantum yield increases. Here it is shown in this graph. On y-axis we have quantum yield or fluorescence, and on the x-axis we have concentration of anthracene, and here this curve it shows the increase in quantum yield, that is phi, with increase in concentration of anthracene, and this curve it shows at a dilute solution of anthracene the fluorescence is prominent, and as the concentration of anthracene increases the fluorescence goes on decreasing, and due to the re-emission of absorbed radiation here fluorescence occurs, and this is the reason behind the low quantum yield. Instead of having the quantum efficiency 2, actually we get the quantum yield 0.5. This is the example of again low quantum yield. Similarly, we have the decomposition of HI and HBr. This decomposition of HI and HBr, these are also examples of photochemical reactions with low quantum yield, and they takes place with this mechanism. Here, the electronic spectrum of HI found in UV region, and hence the primary process is decomposition of HI, and for this phi it is equal to 2. So HI molecule, it absorbs photon and we have free hydrogen and free iodine. This is the primary process. Then in the secondary process, this free radical, it combines with normal molecule of HI and it produces hydrogen molecule and iodine free radical, and then these two iodine free radicals of this one and this is another. Here I2 is formed and the overall reaction is 2HI plus 1H nu. It gives H2 plus I2. As reaction proceeds, the quantum yield decreases because of the thermal reaction, and that thermal reaction taking place here, it is the reaction between here free hydrogen formed and the I2 molecule to form HI plus 1 iodine free radical, and due to this the quantum yield is low. Similarly, the decomposition of HBr occurs. Here the primary process is dissociation of HBr into hydrogen radical and bromine atom. Here hydrogen, it reacts with normal HBr to produce H2 and Br, and then Br and Br combines here to produce Br2, as just we have seen in the above expression, and this is also the example of low quantum yield. Then I will explain you the photophysical processes. Here the photophysical processes means due to absorption of radiation, the electrons are excited, and due to this excitation, the electrons, they jumps from lower energy to higher energy, and during de-excitation, the electrons, they returns back to the higher energy to lower energy, and this phenomenon is occurs in a instantly, that means within few seconds. This is called as fluorescence, and the excited electron returns to the normal state after some time. It is called as phosphorescence, and these two phenomena are called as photophysical processes. And the photochemical processes are by absorbing radiations, electrons are excited. During de-excitations, excited electron returns to normal state after producing some chemical change, and it is called as photochemical process. These processes take place directly or indirectly with the influence of light radiation. And here I will explain you the fluorescence and phosphorescence with the help of Jablonski diagram. Here these are the points we have already learned. Photosensitized reaction, chemiluminescence. Here the explanation of fluorescence and phosphorescence in terms of excitation of electrons. Remember that in the ground state, the electrons are paired. That means one electron, it has upward direction spin, and another electron, it has in a downward direction. And you know, the upward spin, it is denoted by plus 1/2, and downward spin, it is denoted by minus 1/2. Therefore, the total spin for paired electron, it is 0. Total spin for paired electron, it is 0. And when the two electrons, they having upward direction spin here, then the sum here, it is total spin, it is equal to 1. Here, when the electron from ground state, anyhow it jumps to higher energy level due to absorption of photon, and these two electrons, they are with one electron with upward spin, another electron, it has downward spin. Here again, the total spin, it is 0, and such a state, it is called as singlet excited state S1. A pair of electrons with opposite spins but each in different orbital. Here, a pair of electron with opposite spin but in the same orbital. That means, and such a state, it is the singlet ground state. Then this state is termed as triplet excited state, and pair of electrons with parallel spins in different orbitals. And singlet and triplet states, they are calculated by using the spin multiplicity rule. And spin multiplicity, it is given by 2s plus 1, where s, it is the total spin. Either total spin is 1 or total spin is 0. And when the total spin is 1, that means the two electrons, they have parallel spins. Such states are called as triplet states, because 2 into 1 plus 1, it is equal to 3. And these states are denoted by T letter, triplet 1, triplet 2, triplet 3, depending on the extent of energy absorbed. And here, when the spins are paired, that means two electrons, they have opposite spin, and these two electrons in a different orbit. Such states are called as singlet excited states. And depending on the extent of energy absorbed, we have different singlet excited states as S1, S2, S3, and so on. And in the ground state, when the spins are parallel, spin is paired. That means two electrons have opposite spin. Then such a state, it is called as singlet ground state. Here, the excited species can return to the ground state by losing all of its excess energy by any one of path, as shown in Jablonski diagram. Here, the Jablonski diagram, it explains in a very simple manner the phenomenon of fluorescence and phosphorescence. As already I have told you, this is the singlet ground state, and this is singlet excited state. This is singlet excited state. This is S1, here it is S2. This one is triplet excited state. And due to absorption of photon, the electrons, they jump from lower energy level to higher energy level, and this phenomenon we call as a absorption. And when the excited molecules, due to emission of absorbed radiation, it returns back to the ground state. This phenomenon is called as fluorescence. And from the singlet 2 to singlet 1, this phenomenon it is called as internal conversion. That means these are the non-radiative transitions. Here simply electron it returns back to singlet 1 from singlet 2. This phenomenon is non-radiative transition and it is termed as internal conversion. And here when the electron it returns from singlet 1 to triplet 1, this phenomenon it is also non-radiative transition and it is called as inter-system crossing. That means ISC. And when the electrons from triplet 1 it returns back to ground state, this phenomenon is called as phosphorescence. And here we see a time. This phenomenon it requires a time greater than the fluorescence due to spin change of the electron. So the fluorescence phenomenon it immediately stops when the source of light is removed, while the phosphorescence it is continued for some time after removal of the source. And for this reason, the phosphorescence it is also called as delayed fluorescence. I mean, you will have the little bit idea regarding fluorescence and phosphorescence. And in the next lecture, again, I will explain you the Jablonski diagram and what is luminescence, what is chemiluminescence, bioluminescence, etc. Bharat.